In this video, I'm going to go over Cramer's rule. And Cramer's rule is it's a way of calculating solutions for systems of equation using matrices. And the idea is that if we have an example of two systems of linear equations, a system of two linear equations, so here is 2x plus 3y equals 10, and 4x minus y equals 20. So the first thing to use Cramer's rule, you have to convert this into a matrix form. So in the matrix form, we're going to write this as 2, 3, 4, minus 1, acting on x and y. So 2x plus 3y is equal to 10 and 20. So once we have it in matrix form, right, Cramer's rule basically says that the value of each variable, x and y, is going to be the ratio of two determinants. X is going to be the ratio of a 2 by 2 matrix and another 2 by 2 matrix. The bottom 2 by 2 matrix is the original matrix, 2, 3, 4, minus 1. The top matrix, so this is the equation. The first equation is described by 2x plus 3y equals 10. And the second equation is 4x minus y equals 20. This row, this column, 2, 4, right, is associated with the number x. So we can replace the first column that's associated with x with 10 and 20. So basically the same matrix as the building below, but replace the first column with 10 and 20. So here's 10, 20, and the original matrix is 3 minus 1. And so we get a value of 2 by 2 matrix is 10 times minus 1 minus 3 times 20, all over 2 times minus 1 minus 3 times 4. And so this is minus 10 minus 60, all over minus 2 minus 12. And hopefully I can see this on the screen. Let's take a look. Minus 70 over minus 14. I won't reduce this any further, but so this is actually a positive and 35 over 7. So I'll put this 35 over 7. The value of the Y matrix is again the ratio of two determinants. The bottom matrix is the same as the original matrix, which in this case it happens to be 3, 2, 3, 4, minus 1. And the top matrix is we take the original matrix, which is down below, and if you look at the system of equations, right, 2x plus 3y equals 10, 4x minus y equals 20. This column right here is associated with y. We're going to replace this column, second column, with 10 and 20. So we get a matrix of 2, 4, 10, and 20. And this is basically the value of x's and y's. This is a solution of x and y. I won't actually substitute these values in because it's time consuming, but it's a very quick video to show you that the procedure in constructing solutions of systems of equations. You can extend Cramer's rule further, right, to solve systems of equations that are fewer than the number of variables that are unknown. But actually, I'll show it to you in a sec. But let's do a 3 by 3 matrix. So let me erase this board. I won't go through the process of calculating this determinant. I just want to make sure you understand the procedure for calculating x's and y's. Actually, let me try a simpler example so that we can try it out really quickly. So something that's really easy to solve so we don't waste time calculating these things. So how about x plus y is equal to 1, x minus y is equal to, let's make it 2. Okay, so here is a simple solution. We know that if we add these two equations, right, add these, the y's cancel, and we'll get 2x is equal to 3, x is equal to 3 halves. So we already know the answer for 3 halves. And if we substitute this back into for y, we'll see that y is equal to minus 1 half. So we know the solutions already, but let's use Cramer's rule to make sure we understand the procedure. So Cramer's rule says if you have a system of equations, we first convert this into a matrix form. So we'll write this as the matrix 1, 1, acting on x and y, 1x plus 1y is equal to 1. X, which is 1x, minus 1 times y gives you the value of 2. So we already know the answer, and let's just confirm this with using Cramer's rule. So Cramer's rule basically says that x is equal to the ratio of two determinants. So here's our first determinant, which in this case is the original matrix, the denominator, 1, 1, 1 minus 1. And the top is, so this column is associated with x. So if you look at it, 1x plus 1y equals 1, and this is 1x minus y. So this column is associated with the x. So we're going to replace that with 1 and 2 and keep the original matrix the way it is. So we're replacing the first column for x. So this is equal to 1 times minus 1 minus 1 times 2. Diagonals, difference between diagonals. 1 times minus 1 minus 1 times 1. So we'll see this as minus 1 minus 2, and this is minus 1 minus 1. So this is minus 3 over minus 2, which is 3/2. Exactly as we expected. We already knew the answer, so it's nice and simple. So let's try it for y. Y is equal to the determinant of the ratio of two determinants. The bottom determinant is always the same matrix. In this case is 1, 1, 1 minus 1. The top, right, so if you look at the equations, right, like this is 1x plus 1y equals 1. So, and this is 1x minus y. So this column is associated with y. We're going to replace it with 1 and 2. So this is 1, 1, 1 and 2. So we'll take the second column, replacing it with 1 and 2. So now we can solve this to be the 1 times 2 minus 1 times 1 all over 1 times minus 1 minus 1 times 1. So this is now 2 minus 1 over minus 1 minus 1, which gives me, let's see, 1 times 2, 2 minus 1, oh, sorry, 1 over minus 2, which is minus 1/2. And if we take a look at the original, this is exactly what we have, minus 1/2. Okay, so this can be extended further into any size system of equations. So let's try it for 3 by 3, 3 solutions. I'm sorry, 3 variables. So let's take a system of equations. I won't actually solve it, but the procedure, I just want to make sure you understand Cramer's rule as a procedure. So the procedure basically says that, so let me erase this, this is all Cramer's rule. So imagine that we have the following: x plus y plus z is equal to 7, and x minus y plus 2z is equal to 8, and x plus z is equal to 4. Okay, so how do we convert this into a matrix form? Basically, oops, we have a 3 by 3 matrix times x, y, and z. And we're going to put 7, 8, 4. And so let's put in, so what do you multiply by x? Well, you multiply y and z, so we get the coefficients. It's 1, 1, 1 for the first equation. It'll be 1, minus 1, and 2. And then we have 1. There is no zero. There's no y. It's considered 0y, so it's 0. And then a 1. And now we can solve for x, y, and z. So again, x is the ratio, and y is the ratio, and z is the ratio of two determinants. So here's the first determinant. It's a 3 by 3 matrix, the original matrix. So it's 1, 1, 1, 1 minus 1, 2, 1, 0, 1, and followed by a determinant of, so if you look at it, right, this 1, 1, 1 is the column associated with the x. So we're going to replace the first column with 7, 8, 4. So this is 7, 8, 4, followed by 1, minus 1, 0, 1, 2, 1. So we can expand this matrix, sorry, expand this determinant, but I won't do it because it's time consuming. So let's leave it at that. The main procedure is that you're replacing this column with 784, the first column. Y is going to be the same thing. It's going to be the ratio of two matrices. The bottom matrix is exactly the same as the original matrix. So in this case, it would be 1, 1, 1, 1 minus 1, and 2. And I'm getting a little sloppy here. 1, 0, and 1. And Y is the column's second column. It's associated with the second column. If you look at it, this is 1x plus 1y plus 1z. And then the next equation is 1x minus y, z. So this is the second column is being associated with y. So we're going to replace that with 7, 8, and 4, followed by 1, 1, and 1, and then 1, 2, and 1. So this is the determinant you're going to calculate. So we do an expansion of a 3 by 3 determinant, calculating, we get our final answer. Similarly, right, I'm not calculating this because this is really time consuming. It's expected that 3 by 3 you should be able to do by hand, but if you consistently have a lot of mini equations to work on, you should be just plugging these matrices into a computer. There are many websites that offer a little little JavaScript code, right, that calculates determinants of a 3 by 3 or 4 by 4 matrix. If it's a 4 by 4 matrix, really nobody wants to spend time doing that. You'll probably spend like at least 20-30 minutes working on it. Even this, a 1 by 1, you might spend at least a couple of minutes doing it. It's laborious, but if you're consistently doing this, right, you should just be plugging these into a computer and getting the analysis, getting the answers. But anyway, what's Z? Z again is a ratio of two determinants. So here's our first determinant. Again, it's 1, 1, 1, 1 minus 1 and 2, 1, 0, and 1. And then you have a determinant of, so this column, the last column, is associated with the Z. So we're going to replace that with 784. And we're going to keep all the original values. So it's 1, 1, 1 minus 1, and then 1 and 0. And so these are the values for x, y, z that will solve the original system of equations. Now you have to be a little careful on this, right? If you find that the determinant, right, in the denominator, this determinant right here is 0, it means that some of these equations, right, are linear combinations of other equations. In that case, right, they are not solvable in terms of unique solutions x, y, and z. So you have to be careful. If this is 0, you know some of these equations, right, are not independent of each other. So you're saying that some of these linear equations are basically combinations of other equations. Okay, so just be careful. If the determinant of this is equal to 0, you have to stop. So actually in the next example, I'll show you what we can do if you have a fewer set of equations, right, than unknowns. So fewer equations than unknowns. Right now we have 3 equations, 3 unknowns. So I'm going to erase this, and we're going to still use Cramer's. Cramer's is very powerful. We can actually use it to actually do matrix inverses too. But actually I kind of discussed it already in lecture, right? But it's okay. I'll explain that. So it's not really needed right now. So I'll mention it when we need it again. So here's an example of 2x plus 3y minus z is equal to 4, and x minus y plus z is equal to 8. Obviously we have 3 unknowns and only 2 systems of linear equations. Now I can't really solve for x, y, and z as unique values, but maybe we can solve for x, y in terms of z. And so the main idea is that this matrix, right, has to be a square matrix to actually use Kramer's rule. So the first step I'm going to do, right, is convert this equation into another equation, 2x plus 3y is equal to 4 plus z. And this is x minus y is equal to 8 minus z. This I can convert into a square matrix. So here's a square matrix which consists of 2, 3, 1 minus 1 times x and y, but in this case, right, it's equal to 4 plus z and 8 minus z. So the idea is that we're going to solve x in terms of z and y in terms of z. So we reduce these equations into two equations where x is a function of z, y is a function of z. And again, we use Cramer's rule again. It's the ratio of two determinants. So x is equal to det of, so the bottom matrix, right, stays the same, 2, 3, 1, minus 1. The top matrix, 2, 1 is associated with the x value, so I'm going to replace that with 4 plus z and 8 minus z, followed by 3 minus 1. And we evaluate this and we get ourselves x as a function of z. I won't do it because it's the idea that I want to really spend time at. But if you're doing a real calculation, you will spend more time doing this than me, but you'll have to. But anyway, let's do y. Y is equal to the ratio of two determinants. The bottom determinant stays the same as 2, 3, 1, minus 1. And the top determinant is, find the column associated with y, which is the second column. So we're going to replace that with 4 plus z, 8 minus z. And again, we have expand and get ourselves an answer as a function of x as a function of z. We can actually do determinants to calculate matrix inverses and other matrix problems, but actually we don't need it right now, so I won't bother explaining it. So once I start going into eigenvectors and eigenvalues, it'll become more important. Anyway, that was a short video on Cramer's rule.